Okay, year 11. This video, we're going to start to put these voltage half equation values together and talk about these reactions that happen and maybe formally bring in the word spontaneous. I think I've used it before, but we haven't formally talked about it. Okay, so I've titled this one, Why Does Redox Occur? So remember what we've just been talking about. For a reaction to occur, the reduction half equation must be more positive in voltage than the oxidation, or we want something further down on this table to go the front ways, or left to right, and something further up this way relative to it to go in the reverse, or the oxidation way. When we have that, we get a reaction that occurs, or when you put them together, something happens. We learnt that if you do it the other way, you put them together, nothing happens. So the word we use in chemistry particularly is this spontaneous reactions. And we use that in chemistry to say when we put things together, do we get a chemical reaction? Because a lot of times we can put stuff together and nothing happens. So the reactions that happen when we put the reactions together are called spontaneous. And we'll come back to this concept much more deeply in the whole next module. But here it comes into play, and here's a good place to introduce it lightly. So for spontaneous redox reactions to occur, we want something that is more positive in voltage in reduction, going with something that is more negative in voltage in oxidation. Okay? So if we calculate the differences between these voltages, it can tell us if it's going to be spontaneous or not. Okay? So here's some examples, and it's just the examples that I've used earlier, and we've got a new formula here. So a spontaneous redox reaction will occur if the total cell potential is greater than 0 volts, or if it's positive. I'm just rewriting that. I'll write it if it's positive, because if it's negative, it's not going to be spontaneous. Nothing's going to happen. Okay, so this E funny naught total equals the E naught for the reduction half minus the E naught for the oxidation half is a good formula to use. Have I got the formula sheet in front of me? Let me just pull it up. You can't see this, but on our data sheet, we have an equation. Do we have this at all? No, we don't. Oh well, I'll give you a couple of tips to remember it. And I will give you an alternative way to work this out. So our E naught total equals the voltage. So it's just saying that the total voltage for the reaction equals the differences between the voltages. Okay? And it goes in the way of the reduction minus the oxidation. Okay? And the way I remember it is the total cell voltage of the redox equation goes with the read minus the ox. Okay? Or the voltage for the reduction minus the voltage for the oxidation. Okay? So that's how I remember it. It contains the word redox in the correct way around. That's why I like this formula. So here we're looking at our old example between a silver and copper. And we talked about before it works when the silver is being reduced and the copper is being oxidized, or the reverse of the top one. Okay, let's look at the voltage potentials here. For the silver, it's got positive 0.80. It's the greater one. That's good. And for our copper, even though we've still got the reduction one here, it's 0.34, okay? So I haven't reversed it. I've just kept it the same way around. They're both reduction equations, but here I'm saying after it, it's the oxidation one. So we know then as chemists, it's actually going in the reverse way, okay? But I've kept the voltages just as the voltage that's on the page, okay? So what I just need to do is start substituting in this formula. So the total voltage of this reaction is going to equal my half cell voltage for my reduction, which is the silver, which is the 0.80 positive, minus the oxidation half. And the oxidation half is 0.34 positive, so minus 0.34. And put that in your calculator and you get 0.46, or positive 0.46. Notice I put the positive in there. I'm reinforcing that it's greater than 0. Okay, because it's greater than 0, the reaction is spontaneous. So it's saying that if you take silver ions in solution and you dunk a piece of copper solid metal in there, you're going to get some stuff happening, like the copper going into solution and turning blue, and the silver precipitating out on top of the copper and being a black substance. Okay, let's contrast that with what would happen the other way around. Okay, what would happen with the other way around? Okay, what would happen if we want the copper to be reduced, or we had a solution of copper 2 plus ions, or that blue, like the blue copper sulfate solution, yeah, and we wanted to dunk in a solid piece of silver and oxidize it to silver plus. So we put a solid chunk of silver in there. Let's see what happens. So we want silver to oxidize and copper to be reduced. So let's calculate our voltage, or our total cell voltage. We've got our reduction half because we want copper 2 plus to reduce, so it's plus 0.34, and we want silver to oxidize, so we're going to minus that 0.80 away, or minus the positive 0.80. Put it in your calculator and you get negative 0.46, or the opposite sign to the other one. Okay, it's less than 0. So that's saying it's not going to be spontaneous. It's not going to happen. Okay, so here we've got a mathematical way to express what is going to happen and what's not going to happen. Okay, notice if you swap them around, you just get the negative value of what you had before. All right. Okay, so I think I've just got another example. I pulled up the old copper and iron one that we've been talking about all through this chapter. Okay, so we talked about copper being reduced, or copper, like a copper blue solution being reduced in the presence of an iron solid. Okay, so this one going forward and this one going reverse. And we said that's going to happen because if the reduction half is more positive, it is 0.34, then the reduction half, negative 0.4, it will work. But let's start putting numbers to it, okay? So here, our reduction half is our copper, so we put positive 0.34 in, and our oxidation half that we're going to minus away is negative 0.44. So we're going to put negative 0.44. Expand that out, we get 0.34 plus 0.44. So we get 0.78 volts. It's greater than 0, so the reaction is spontaneous. Okay. However, we're going to swap it around. Okay. In this case, I'm talking about we want iron to be reduced, or we want this one to go forward and this one to reverse. We solve, looking at the table, that's not going to happen, but let's use the numbers. So iron to be reduced is negative 0.44 minus the positive 0.34. It's going to be minus 0.78. That's non-spontaneous. So swap those conditions around between solid and aqueous, you're not going to get a reaction. I thought of something there too. I remember at university, first year uni, one of my good lecturers explained it as thinking, instead of the E naught total equals E naught reduction minus E naught oxidation, is you're finding the difference between the two numbers. Okay, if there's a positive difference, it will work. If there's a negative difference, it won't work. I don't know if that will help. I didn't explain it anywhere near as good as he did. Use the formula. Okay, let's do some examples. Give the redox equation for the reaction between copper ions and magnesium metal. Okay, so copper 2 ions, there's only one way that they can go, and that is to be reduced to copper solid metal. Oh, why did I just put an ion on there? What a duffer. Copper solid metal. Okay, let's find it on here. It's always good to orientate yourself on the table. Copper 2 plus 2 electrons, so it's that one going forward. And what are we talking about? Magnesium metal. Okay, well, magnesium metal, if it's taking part in a redox equation, can only be oxidized. It can only be oxidized to magnesium 2 plus. and you've got 2 electrons there. Let's find it on here. Here it is. Okay, notice it's in the opposite way there. So we've got, it's saying copper is being reduced, magnesium is being oxidized, or copper's going that way, magnesium's going that way. Okay, we've got the conditions for a spontaneous reaction because our more positive one, or the one lower on the table, is going the forward direction, and the one higher up on the table is going in the opposite direction. Okay, we're going from magnesium solid over to that way. Okay, so we know we're going to get a reaction here. It's going to be a positive, but let's make sure. E naught total is going to equal our E for the reduction minus E for the oxidation, redox, equals, our reduction is the copper, so it's positive 0.34 volts, minus our oxidation is negative, I'll put a bracket around it, negative 2.36. Okay. Oh, now I'm zooming in because I left it for too long. What I was just going to say is I like to put brackets in here because you don't want to get mucked around with double negatives and stuff like that. Be mindful of that. Calculator. Help if I had one in front of me. Here we go. Can't even turn it on. There we go. I can do it in my head much quicker. Isn't it positive 2.7? 0.34 plus 2.36, 2.70. 2.70 volts. Okay, don't forget that second zero, even though your calculator won't put it in. Remember, plussing and minus, we've got to conserve the decimal places. So that's greater than 0 volts. So, C, state whether the reaction is spontaneous and explain why. Well, reaction is spontaneous as E naught cell or E naught total, same kind of thing, is 2.70 volts, which is greater than 0 volts. Okay. Same type of thing, I've just changed it up. Give the redox equation between sulfate ions. Well, I talked about them here on the table. There they are. So we're talking about this way. There's only one way they can go. Sulfate can be reduced to sulfur dioxide and water. And lead metal. Where is lead hiding? Oh, just 2 above there. Okay, lead metal can only be oxidized. Okay, so you can see that the reduction is lower down on the table than oxidation. So we're going to get a spontaneous reaction, but let's do it mathematically. So our 2 half equations is, we've got our sulfate, and just copying it from the table, our 4H plus, and our 2 electrons are going to sulfur dioxide and water. Oh, how many? 2. Straight from the table, 2 waters. And for our oxidation half, we're just flipping our reaction here around the other way. So our lead solid goes to lead 2 plus 2 electrons. Oh, did I give the full one? Oh, I don't think I gave the full one back here. That's okay. Should I get distracted now? Give the redox equation. Oh, I would have been marked down. 2 being given, 2 taken, so we can just add them together. What a duffer, I forgot it. So copper solid plus magnesium 2 plus aqueous. Okay, back to the one where we were. Sorry about the distraction. Okay. On the left-hand side, we've got 2 electrons. On the right-hand side, we've got 2 electrons. So we don't need to multiply anything. We just need to add them together and cancel the electrons. So sulfate plus 4 protons plus lead solid goes to sulfur dioxide plus 2 waters plus lead 2 plus. All right. Calculate the total cell voltage. Okay, our formula, E naught cell, or total, E of the reduction minus E of the oxidation, so we got redox in the right way, which equals, our reduction is our sulfate going to sulfur dioxide, which is positive 0.16 volts, minus our oxidation is lead, negative 0.13. Okay, or it's the difference between 0.16 and negative 0.13, so it's going to equal 0.29, isn't it? Or 0.16. My recommendation is, in the exam, don't think you can do it in your head, put it in your calculator. Less mistakes will happen. 0.29 volts, that's good, and that's positive. So the reaction for part C, reaction is spontaneous, hopefully I'm spelling right, as a cell equals 0.29 volts, which is greater than 0 volts. Alright. One last example. I pulled up a past HSC question. Alright. It's not calculating the cell voltage though. Ah well, let's do it anyway. It's still putting into practice redox equations. Okay, the following experiment was performed to investigate the relative activity of metals. A beaker contains some volume and some concentration of copper sulfate. So we've got copper 2 plus, and we've dunk a whole chunk of zinc in there. Okay. After several hours, the dark blue colour of the solution had become lighter, and a red-brown deposit had formed on the zinc metal. Account for the changes. We've got copper 2 plus going to copper solid. So, the observation of the red-brown deposit is that copper is being reduced to copper solid and plating on the zinc. Okay? And after several hours, the dark blue colour of the solution become lighter, or we've lost concentration of copper 2 plus because it's been precipitated out. Okay, so they're the two observations and why. The red-brown deposit was removed and it was found to weigh 0.325 grams. Calculate the concentration of copper sulfate remaining. Ooh. First thing that we need to do is a balanced chemical reaction. So 2 halves, let's start with. We've got copper 2 plus 2 electrons going to copper solid. And we've got zinc solid going to zinc 2 plus, being oxidized, plus 2 electrons. So our overall chemical equation is nice and easy because we're giving up and taking away 2 electrons. Let's just add them together and cancel out the electrons. Nice and simple there. Okay. Alright. So what we found and what we're given in the question is the red-brown deposit, which is the copper solid, formed 0.325 grams. Okay. It's asking essentially how much of the copper 2 minus it took out of solution. Okay, so let's find out how many moles of copper solid that is. So 0.325 grams divided by the molar mass of copper is at, where's my periodic table? 63 something? 25? 63.55. Oh, 63.55 grams per mole. Put it in our calculator. 0.325 divided by 63.55. So I get 5.11 times 10 to the negative 3. I'll keep those numbers in my calculator. Moles, units. Okay, so it means we must have lost 5.11 times 10 to the negative 3 mole of Cu2 plus because we gained that number of moles and it's a 1 to 1 stoichiometric ratio. So we must have lost that many moles, okay? How many moles did we have to start off with? Mole initial of copper 2 plus equals the concentration, 0.050 mole per litre, times it by the volume in litres, 0.2500 litres, 0.05 by 0.25. So that is 0.0125 mole initially. So mole final, so our final number of moles of copper 2 plus is going to equal our initial minus how much was consumed to make the solid. So it's going to be 0.0125 mole minus the 5.11 times 10 to the negative 3 mole. Okay, minus 5.11 times 10 to the negative 3, 0.00739 moles. It's asking us for our final concentration. I'm assuming our volume of liquid hasn't changed, so it's still 250 ml. So our final concentration, not of G, of C2 plus, equals our number of moles, 0.00739 mole on our volume, 0.2500 litres, divided by 0.2500. I get 2.956 times 10 to the negative 2 moles per litre. And I need to report that to 2 sig figs, so it's 3.0, if I can write that down. Oh, it's not liking. To 2 sig figs. Alright. Oh look, when I did the problem last time I got the same one. So now you can do worksheet 311 and have plenty of practice calculating reduction cell potentials and stuff like that. And next time we'll talk about this one.